because I tend to think through the code, but if that's not for you, don't worry, you can just follow the words or the maths that come up. So let's say I have an atomistic system like that, right? Here's the atomic coordinates, the Cartesian coordinates of that system, and if I perform a rotation now, you see I'm rotating around the x-axis, these are the numbers that are being represented in this table for the atomistic positions. So clearly that's changing if I translate it. So I'm just going to move the x coordinate, right? That changes. And if I now swap, so you see the one that was at the top moves down. It's okay. Okay, well, I'll speak over it and hopefully. So you can see that I'm doing these three operations, right, and the numbers are changing. So this is definitely not a good input to give to a machine learning model, right? Because as I do things that shouldn't change the property, the machine learning model sees something completely different. So that's clearly not what we're after. So how can we deal with the situation? So permutation, well, let's say I just sum along these columns, right? The x, y, and z, I sum them all, I get some numbers. And so now, as I swap the position of the first atom with the nth atom in the list, that representation doesn't change. So that's good, we're getting a bit closer. Rotation, obviously, we're still sensitive to in translation. We've not done anything to that. Okay, that's fine. So for translation, the next thing we can do is, for example, before we feed the representation to the machine learning model, we can just subtract the center of mass, right? That's the simplest thing we can do. And that clearly will make it translationally invariant because we will just center it wherever the center of mass falls. So as I move it in space, the thing doesn't change the representation. But we still have the variance to the other things. Rotation, we can take, for example, the norms, right? The lengths of all of the vectors, and just feed those to our model. And obviously the lengths as I rotate a rigid system aren't going to change, right? So as I do that, the representation that we're plotting there doesn't change. So let's put it all together, all three of those in one. So I now do those three things I just did in the previous slides, and now I have one number at the end that is completely invariant to all of those transformations. Clearly, this is not a good representation, right? So I've taken 3n atomic coordinates and I've condensed them down to one number. They have other properties that I said I wanted, but it's obviously not invertible, right? This is not a bijective relationship with the original atomic coordinates. So we need to do a little bit better than that. I think the easiest way to explain this, at least for me, is to think about, the way that we would describe just a function or some data in space, right? We calculate, or for example, we sample the heights of people, right? We plot that on a graph. What are the first things we would do with that? Well, probably to represent that, to communicate that to someone else, we would calculate the mean and maybe the standard deviation and then higher order moments. And it turns out that, you can take the 0th order moment of a function, which will just be the total integral, the first moment, which is the mean, the second moment, which is the variance. But this is an infinite series that can go up. And from a sort of visual point of view, what that's doing is describing the shape of the function, right? As you go to higher order moments, it tells you the skewness, the kurtosis, so it's telling you how this function varies in space. And you can go up forever, and if you do that, you will calculate all the moments. And there's even a theorem that tells you, well, if you have a collection of moments up to infinity, that will uniquely define the function that we started with, similar to a Taylor expansion, let's say. Okay, so that sounds promising, but we're not there yet at a set of ways that we can describe atomic positions. So what we can start with is first extend this to 3D, right? So now I've got x, y, z coordinates, and I'm going to raise them to the various powers, right? So depending on the order of the moment that I want to go to. So the first order moments are these things. The second order moments become a matrix, which is actually the inertial matrix. And you can keep going, right? And there'll be higher and higher order tensors. What we don't yet have is permutational invariance, right? So to get this, what we need to do is represent our system of atoms as some function, right? So here we've got some function, and we're going to calculate the moments of that thing, which then gets stored in this tensor. Or you can think of that as being just, some function that you project onto a basis set, if you like to think in bracket notation. What kind of function? Well, it's actually fairly straightforward. This has been done for many years in the literature. So imagine we have the atomic positions here, the actual Cartesian coordinates, but we want to treat it as a single particle function, right? And this is actually the same trick that DFT relies on. So we're going to write a function now that's no longer a function of all of the individual coordinates, but it's actually just a function of r in space. And what are we going to put at each point where the atoms were? Well, you can just put a delta function. Or if you like, you can put a Gaussian. That's what's used in SOAP and gap gap machine learning models, basically the same thing. So we've gone from any number of atoms that we want to go up to, whatever n here, to just a single particle function. So we're doing well. Now there are various reasons that we'll see in a second why it's actually good to use spherical harmonics as the basis instead of polynomials that we started with. Spherical harmonics, if you're not familiar, are just these special functions that are also eigenstates of angular momentum for quantum systems, say the hydrogen atom, but they can also be used as just generic mathematical functions, and in fact they correspond well to the irreducible representations of the rotation group, which is why we use them. But for now you can just see them as functions that we're going to project our atom density onto. So what am I talking about? Well, that atom density that I started with here, I'm just going to do the full integral of that onto my spherical harmonics in some radial function, and that gives me this tensor that now sits there and I can use to do other things. And actually, one of the reasons to use spherical harmonics is that they're an orthogonal basis set, right? Which means that if I do this projection, it's basically like a Fourier transform, but in angles rather than in space, I can always do the inverse and reconstruct the original function that I started with here. So that's, you see, if I'm already thinking about universality, that's something that I'm going to want to build in from the start. And then, okay, there are many possible choices for this radial part that I didn't really talk about. The spherical harmonics are fixed. We can't change them. They are what they are. The radial functions we can choose. I chose Zernica functions, which is an orthogonal set of polynomials. But this function basically just encodes how far away is each atom from the other atoms, right? That's all it's there to do. So let's see what this looks like. So if I take that original molecule that I had, so I've performed the Fourier transform, calculated these moments, and then now I've done the inverse, and I just plot the density, the atom density now, of the original molecule, and you can kind of see the shape there. So okay, that's kind of good. We're making progress. And in fact, if you choose your basis set correctly, this can be convergible, right? So this is the maximum order to which I expand the spherical harmonics and the radial functions. And you can kind of see it's like upping the resolution, right, of an image. If I have 15 of them, I've actually plotted the molecule. It's a urea molecule that I've used on top of it. So you can see, by this point, it's already fairly well represented. As I go lower and lower, it's a worse and worse representation of the original set of atoms that I started with. So that's kind of a visual way to show you, how high in my expansion should I go before I cut, and that's it. So how do I get these invariants, right? These are these rotation, translation, so on, invariants that I want. So if I just plot the actual spherical harmonics themselves, they are obviously not, the expansion coefficients, which I'm plotting here, are not invariant to rotation, right? As I rotate my atomistic system, this thing is going to change. So it doesn't have that rotation invariant that we want. However, what we can do is start to do tensor products between these spherical tensors, right? And it's a bit hard to see here, but what I'll do is I'll zoom in, right? So here I've taken the tensor product, a single tensor product, between two spherical tensors, a tensor with itself. And if you look very closely, here in the top left, this pixel doesn't change as I rotate, right? Right there. The rest of them do, but this one doesn't. The reason for that is that transforms as the L equals 0 spherical harmonic, which is just a sphere. It's something that doesn't change it's the numbers when I rotate the system. But okay, but I'm still stuck with one number, which I said I didn't want. Well, what I can do is take these expansion coefficients and start to do higher and higher order tensor products. So by this notation, I'm doing a tensor product at some angular frequency L of the spherical harmonic expansion, and then I keep only the L equals 0, the scalar part, from that thing. So I can collect more and more and more. And if any of you have worked in the, particularly the atomistic machine learning interaction field, SOAP descriptors, for example, would be degree 2, and then you have the bispectrum, which is used by snap potentials, which has degree 3, and then very few go up to degree 4. ACE descriptors, for example, do. But in any case, point is we can keep going up and collect more and more of these that are very similar to those moments I described at the beginning. They describe the shape of this function in space in a way that is unique. So if I collect all of these, right, and I'm keeping only the first 50 here, you can see that now I really have a fingerprint that does not change as I rotate my atomistic system, right? And it also doesn't have this, as I permute the atoms, it also doesn't change because I did this original sum of all the delta functions, right? So a sum is obviously permutationally invariant. So this is actually great. This gets us a long way, And this is the basis for a lot of the historical work and current work on descriptors for to be fed into machine learning models of atomistic systems. So to give you a flavor of what that kind of looks like, you know, it's a unique fingerprint that essentially identifies what the 3D shape of this atomistic charge density is, this atomistic atom density is in space. And then, you know, of course, we have to ask, well, how do we use this? Well, all these X's are one fingerprint of one local atomic environment around a single atom, right? So I'm going to take some atoms of my system, go up to some cutoff, keep all the neighbors that are within it, and calculate the fingerprint, and then I can feed that downstream to my model, right? A neural network, a Gaussian process, whatever you like. And if I'm learning energies, well, for example, energy is a total, there's no such thing as a atom local energy. We only have the total energy of the system. So we would just predict some local atomic energy for that system, even though it's not physically defined, and then sum all of those at the end, and then get the total energy and compare that with our reference from DFT or whatever it is. And of course, we can plug in that final energy and do derivatives of it to get the forces and add that to our loss function, and so on and so forth. So the descriptor that I described, I was particularly interested in having a descriptor that's invertible, so I can turn that fingerprint back to the atomistic configuration, which I won't discuss here. But I also tested it on predicting energies, for example, against some of the common ones. So the one I created is called Milad here, and it performs pretty much as well as most of them, apart from maybe GAP and NPT, because they use a different regression scheme. Whereas the closest one to mine is this NNP. It's also a neural network-based regression scheme. So it gets energies and forces pretty much as good as most of the things that were out there until maybe a couple of years ago. And I'll discuss that in a second. Okay, so we now have a way to go to a set of invariant descriptors of any atomic configuration. And even though I won't discuss it, I can also go back to the atomistic configuration. But we might ask the question of, but hold on a minute, let's go back to this image, right? So we have these tensor products that we did. What about all this stuff? What about all the rest of this thing? Is there anything that we can do with this? Well, it turns out yes, and this is started a sort of whole subfield, let's say, that's only really come out in the last 4 or 5 years, called equivariant machine learning models, right? And I'll discuss what that is. Okay, so because we were looking at energies, right? Energy is a scalar, so it doesn't change when we rotate our function. And that means it's invariant to that transformation. By invariant, if I'm to formalize this, I would mean I'm learning a function. Theta is the weight of my neural network model or whatever I like. And I'm putting in my input. And now if I perform a transformation of that input, so for example, rotation, it will produce the same output as if I hadn't rotated it at all. And formally, for it to be invariant, that has to be true for all members of the group G, which is O3, the group of rotations. But anyway, you get the point. It's something that doesn't change as I rotate or transform my input. Equivariance, on the other hand, just adds a little bit more to this. It says, well, okay, what happens if I put in something that isn't just a scalar, like a vector? If I rotate that vector here, and the output of my function is now a vector, then if I rotate the input, I should get the same output as if I rotate the output of the function with the original input, right? So I can do it sort of in either place. And that needs to be true for all members of the group G. And it turns out doing this internally gives a state-of-the-art data efficiency. What do I mean by that? Well, for example, even for energy models, where, yes, we're predicting a scalar, but internally the model will have an equivariant representation that it carries with it throughout the neural network, say, or whatever process you want. People are showing that, and this is kind of a summary of results from the community, these invariant models, which are now a bit older, which are L0 because it's the L equals 0 Spherical harmonic, have a sort of learning rate like this. So that means if I'm showing it more and more examples of training data, the error, whatever it is, the error in the forces or energies, goes down with some slope. If I change the hyperparameters or change the model, it might move this line, so the intercept, but it's not really fundamentally changing the slope. And what we want is, of course, something that has a steeper slope, because what that tells us is we can actually either get a more accurate result with the same amount of data, or get a result, of the same accuracy with much, much less data. And as physicists, that's exactly what we want, because the DFT or the experiment are going to be extremely costly. So here I'm sort of showing, well, as you increase the internal representation, the maximum angular frequency that you keep in your representation into the end, you can actually turn the slope down and get more and more data efficiency essentially for free, right? It's the same data, but you get a better model. Yeah. Yeah, it increases exponentially. So the descriptor size will become very large, and therefore everybody who does this will either do some kind of culling, right? Because actually there are many descriptors, and that's part of the work that I did, that are dependent on each other, right? So either they're linearly dependent on each other or non-linearly dependent, and so you can eliminate those. But even so the descriptor I showed you, the invariant one, has 113 numbers. If you go to these equivariant ones, you would at least square that or more, but we're still very, very low compared to, you know, the large neural networks that are used. I'm not even speaking about LLMs, just, you know, large neural networks used in industry will have millions of parameters. So Mace and Ace are these equivariant descriptors, right? Or they can, I mean, Mace, the descriptor is effectively the neural networks learned in there. Ace, you calculate it beforehand, and indeed they will cull a lot of them. And then Ace, they will typically use with a linear regressor, so it's very simple to do the regression, so it doesn't matter if you have so many. So indeed, but this is a good point, so you'll for sure be paying a price in your training, right? In terms of your training will be more costly to do. But typically, you know, for me, when I do these equivariant models, it takes a few hours to train, maybe a bit longer. That's nothing compared to the DFT. Yeah, but it's true. These will increase in the quantity of descriptors, let's say, that you have exponentially with the Lmax, which is why people tend to stop at 2, sometimes 3, because the gain also is diminishing. So yeah, one of the pioneering models that came out a few years ago now is NeckWhip that used these internal equivariant representations. And to kind of labor this point, you know, they trained on 0.1% of the data for different phases of ice that was used to train a deep MD model, which was and still is one of the more widely used invariant models in the community. And with 0.1% of the training data, they achieved basically the same accuracies, right, for energies and forces. So that's a real gain. And if you can get that, even if your training cost is much higher, typically you will take that. So just to give you a feeling again for what this all means, right? It's quite abstract when we talk about the group theory and all these parts, but actually, intuitively, there's not so much to it, right? So if we go to just a fully connected layer in a neural network, so we just take, you know, some inputs are going to have an all-to-all connection and then produce some outputs to the next layer in my neural network. I can represent this like this, right? Some inputs dot producted with my weights, and then I pass it all through some activation function like the sigma, you know, the things that you see always, non-linearities in my neural network, to produce some output. The only difference in an equivariant layer will be that, you know, if I have, say, 2 vectors that are my inputs, I will take the 2 of them, perform a tensor product, and then that produces this rank 2 tensor, and I extract the so-called irreducible representations of this. But all that means is I take, for example, the diagonal of this thing will always be a scalar, so that's what this thing is, an L equals 0. There's a diagonal part here that will be a vector, and an off-diagonal, an anti-symmetric part that will be an L equals 2 vector, so it has dimension 5. Now all I need to do, is to keep this equivariant, is to make sure that when I have weights, I only apply them to the whole quantity, the whole irrep at a time. So I have a weight for that, a weight for this whole vector, and a weight for that whole vector. The reason for that is that equivariance requires that I can't rotate my inputs. I can only scale them. So here I can arbitrarily rotate this thing. I can have different weights for different components of my vectors. Here the whole vector gets multiplied by some weight, and that preserves this equivariance while simultaneously reducing the number of weights, right? From 6 to 3 here in this trivial example. And that might give you an intuitive feeling for where this data efficiency comes from, right? Where before you might have all these, you know, all-to-all connections, many weights. Here we've just got 3 producing these outputs, and that's sort of schematic of 2 vectors being inputted to a layer in an equivariant network to produce an output. Okay. Any questions on that before I kind of move on to some applications or, yeah, show you what we can do with this? Cool.
Sorry, so I just ask, can you also create a descriptor center on a grid point?
An arbitrary grid point instead of an atom.
Just an arbitrary grid point, so you can do like grid-centered quantities like charge density,
sure,
electrical potential, stuff like
yes, absolutely. Yeah. So yeah, for charge densities it would be particularly good. I'm trying to think if we've done this before, not on grid points, but we've done things like between atoms for finding Vannier centers and things like this. You can absolutely do it on grid points. The thing you'll definitely encounter there is that, you know, typically you'll have many more grid points than you'll have atoms. And that's where this cost, yeah, so that's where this cost will start to kill you from doing the equivariant tensor products. So you might have a computational bottleneck there. But in principle, yeah, absolutely, you can do it on grid points.
Yeah, that's interesting.
More questions?
Sweet. Okay, and so really to sum it up, the way I think about these things is, you know, the regular learning, no symmetry awareness, no physics, no maths in it at all, is, you know, you just put in the Cartesian coordinates. The invariant one, you throw away your reference frame and you only calculate invariance of the system. And the equivariant one is kind of like as if you kept all of the positional information, both the invariant part and your global coordinate frame with it. That's one way to kind of think about this if you're not yet familiar with how these things work internally. And that's kind of contrasted with the way things used to be done, especially by computer scientists, which is data augmentation, where they would just, you know, rotate the thing many hundreds of times, feed it to the neural net and show it the same label, the same prediction to try and force it to learn that. Now we just show it one example and it learns all possible rotations of that thing, including of any vectorial or tensorial quantities. Okay, so what can we do with this? So one of the group that I was in with James is very interested in electronic structure theory and pushing it beyond what it can do today. And that obviously means extending it to try and fix problems that where DFT doesn't necessarily work well for certain elements, certain classes of systems. One of the things we've been looking at is the electronic structures for systems that contain transition metal elements. And these are particularly poorly described in regular run-of-the-mill DFT, PB, these kind of functionals that people tend to use. And that's particularly problematic for a lot of different applications. And for us, it was particularly batteries that we were looking at. Thankfully, there's been a lot of schemes that have been developed to correct some of these problems with DFT, including in the Nicola Mazzari's group where we were. And the particular one that we're looking at is this thing that comes out as a consequence of a self-interaction error that's made in DFT. I don't have time to describe all of it, but essentially DFT isn't aware because it also treats all of the electrons not as individual points, but as charge densities, just like we had the atom densities. And so when you do an integral inside the charge density, the exchange correlation functional calculation, you're actually integrating twice over density with itself, because you don't know this is electron 1, this is electron 2. You just end up doing an integral over the density with itself. And the consequence of that is that systems like this, right, say I take an olivine, and I've got different amounts of lithium that I can put in this thing. So I'm charging up or discharging a battery. In DFT, what will happen is that the oxidation state of this manganese will, so there are 4 manganese here in this unit cell, the oxidation state will change together, right? It will change in a non-integer amount until it changes from, I think this is, a 3+ to a 2+, right? Clearly that's not physically correct, right? We can't have a non-integer oxidation state. The electron either needs to be there or it needs to be gone. So HSE06, which is a much more expensive technique, can capture this correctly. So it gets this sort of digital change in oxidation state, if you like, as I add more and more lithium. And that's exactly what we want. And there's this scheme called Hubbard corrections that is much, much cheaper than something like HSE that will actually correct this self-interaction error in DFT to produce this quantitatively correct behavior, and simultaneously also give us a quantity that we're super interested in, the band gap, in much better agreement with experiment. So that's another reason to do this. So how does it work? Well, essentially, it's nothing other than a correction to, you take your normal DFT and you make this correction to the energy. So it's not a functional itself. It's essentially a correctional to the energy that you get from whatever functional you have. And the general form of it looks like this. Essentially, there's a Hubbard U parameter, which is an on-site parameter. So it favors localizations of the electrons. And it's going to correct, these are occupation matrices, which tell you, how many electrons are in the valence manifold of that atom, so typically the d states. And then there's a v part as well that acts between two pairs of atoms, so that you can think of that as being, say, the manganese and the oxygen, to favor hybridization and correct some of the over-localization that the u part does. And then effectively that's all you do to correct for this, let's say, mistake made in DFT, this oversimplification. But of course, we need to answer the question of, well, where are these u and the v coming from, right? These are just scalar numbers. We need to plug those in from somewhere. And this is where self-consistent schemes allow us to do actually a self-consistent Hubbard calculation to get these values out. So in essence, what we're going to do is calculate the occupation matrices that tell us, how many electrons are sitting in the d shell of that particular atom. For those of you that worked with these plane wave codes, you'll have your plane wave states that you project onto some localized orbitals. So these are also spherical harmonics to figure out how many electrons are sitting in the d shell. And of course, these spherical harmonics are just sitting on each atom. They're centered on each of the atoms, right? And then we can do a so-called linear response calculation, which effectively tries to correct there's a curvature that leads to this of the energy as a function of the occupation of each of those manifolds that leads to this self-interaction error, and this fixes it by linearizing that, so making it either be a 2+ or a 3+, trying to force that energy to be non-convex in between, say, 2.5+, which doesn't make sense. It's quite a complicated scheme, and you can look up the papers of Yuri Timrov if you're interested. But the thing that was really bothersome for me is that this is really, really expensive, right? To do this self-consistently, it's going to cost, this one linear response calculation is going to cost about 20 times the cost of one of my DFT calculations. And it's even worse than that because I have to do this multiple times, right? So if I start with some guess of this, let's say u value, I start with the guess, I calculate it, I update it, I run it again, and then I do the calculation again, I update it, and I keep going until this becomes flat, so it's now self-consistent. The atoms were allowed to move at each step, and now I have a u value that's sitting with a self-consistent structure and energy. So now I've gone, each of these is going to cost me 20 times my DFT calculation, so it's going to be 80 or 100 times the cost of a DFT, so you're going to really want to know that property to go to all this effort to calculate it. Can we accelerate this with machine learning? Can we replace, just start with the original crystal that we have, put in our machine model and predict what the U and V value should be, and then geometry optimize, and then we're done. So we're going to use the equivariant neural network models that we developed in my group to do this. The translation invariance is already there. The rotation invariance comes from the equivariant nature of the network, and the permutation of labels we'll have to do a little bit of work to get. It's not too hard. So the rotation, we can take these occupation matrices. So this is just going to be a 3x3 or 5x5 matrix. We can decompose this into the irreducible representations, which would be a direct sum of, say, an L equals 0 part for an L equals 1 plus an L equals 2, or if it's it depends if it's a D or an F, this sequence of irreps. And we can feed that straight into the neural network library as the input, right? These are the descriptors, if you like. The next thing we need to worry about is permutation invariance. So the only real thing that we have here that we didn't have before is a spin label, because these are spin polarized calculations, so we can have a spin up and down channel. Obviously, if we swap what we call the spin up and down, nothing changes. The physics is the same in this case. So we need to create a polynomial that is invariant to that transformation. And I'm just going to create two, a sum of occupation matrices of the up and down and a tensor product between them. Both of those are permutation invariant things that can then feed straight into my model. Okay, so now we have the building blocks. This work was done with Austin Zadek's, Luca Binci, and Yuri Timrov, who developed essentially the calculations that allow us to get the labels for our models in the first place. And the model is going to look like this. I'm going to have two different models, one to calculate a U parameter, because that's just per atom. It's just one atom at a time. I don't know or see what's going on with anything else other than through the occupation matrices around me. And the inputs to that model are going to be the previous U parameter that I used for the calculation, the element that's there, and the two permutationally invariant occupation matrices, permutationally invariant of the spin channels. And that's going to go through a series of equivariant layers that I showed you one of before, and then I'm going to produce a final output U value. Similar story for the V, but this time I have two atoms interacting with each other, so two different elements, two occupation matrices around each atom, and then a V value that sits, if you like, on the edge between the atoms, and a distance between them. So those are the only inputs to the model, and the output is the Hubbard V parameter. For the data set, we've got not a lot of materials, 27 different crystal structures, but then there are ones where, for example, this one, we have 5 different lithiation states for each of these, and then a few of these. So it's a fairly modest data set by, let's say, atomistic machine learning standards. And when I total it up, and then I have to do some deduplication because there's a lot of very similar oxidation states. So to make it a fair test, I have about 1,300 inputs for the, or labels, let's say, so outputs for the U, and many more for the V, because this is a pair quantity, right? Every pair of atoms has a V that I can use. And then I'm going to do a normal thing, kind of split it up, keep 20% back that I don't show the model, and train on the remaining 80%. And then when I do this and do a parity plot, so I can see like, okay, this is the prediction from the very expensive density functional perturbation theory calculation. This is the prediction made by the model. And, you know, the energies are pretty good. They're not on the scale that we're used to seeing for interaction potentials, you know, 1 millieV per atom or 5. They're in the hundreds of millieV atom. However, on the scale of the parameter itself, they're still very reasonable. They're, let's say, 5%, 6% of the U value. And the V is slightly worse in terms of its distribution, but it's still really very much within what would be good enough for most people, unless they really want to calculate something very, very precisely. So, and we also wanted to check, you know, okay, that error that we're getting on the machine learning model, we don't really care about the error in the energy, right? That's not an observable we're going to measure. We care about things like open circuit voltages, for our case, looking at batteries, or the magnetic moments. And for those, the differences that we make when we use the predicted values from our model versus what we would get from the linear response calculation are almost nothing, right? So downstream properties that we would screen for are essentially bang on, even with that small error. This one I think I'll skip, but I wanted to just show you one thing that's seems to be a property of these equivariant models, is that they can transfer quite well to systems that they haven't seen, or at least configurations they haven't seen. So here I'm going to take those olivines, and as I said to you, there's different amounts of lithium that I can add to these, right? So what I'm going to do is, let's say, I'm going to train the model on this one and ask it to predict all of the rest of them and see how well it does. So this is really trying to predict the different oxidation states that it hasn't seen before. And then this one and all the others and all possible permutations. Then I'm going to train on 2, and then all possible permutations of the others, and so on. And the results I get are like this. So if I only show it 1, it's not doing as well. And when I say as well, I'm using the blue line as a reference, which is when I show 80% of all of these and predict on the remaining 20. But then by the time I've shown it 2 out of the 5 of these, it's already doing a very, very good job. And the story is fairly similar with, so I think I haven't labeled these, but this is the iron, this is the manganese, and then we have a mixed olivine where we have both iron and manganese on the different sites. So why do I care about this? Well, it shows me that, you know, I don't need to, if I really want to study the systems, calculate data for all of these. It's enough to show maybe a couple of different lithiations, and then the rest will be predicted well by the model, even if it's extrapolating quite far from what it's seen in the training set. And this is really kind of the, maybe not holy grail, but it's certainly a property that we'd look for in a model that we want. Okay, so I'll give one last example of what we can do with equivariant models. If there's any questions about that part, we can take them now. Otherwise, at the end. Okay, so another thing, so there we were using a tensorial property as the input to our model, right? And then predicting a scalar quantity, U or V. Can we do the opposite? Well, of course. So let's say we want to predict something like polarizations, or in my case, so we have a system where we apply an external electric field that produces a polarization of the atoms, and there will be a response to that polarization. There are various things that we can calculate, but one of those that's very common is the Born effect of charges. So you can see the enthalpy as a response of changes in the electric field or changes in the positions of the atoms. That's going to be this rank 2 tensor. And then another quantity that we can calculate is the Raman tensor, which is just now 3 derivatives of the enthalpy, twice the electric field and once with the positions. So now we're putting in atoms to the model, and we're predicting tensors as the output to the model. And we start, as always, we decompose this thing into the irreducible representations, which are just there. but it's the same trick. And we plug it into our model, right? So we've got our atomic positions, the species, and this all goes through, in this box is hidden a graph neural network that does equivariant tensor products, similar to MACE, if any of you have used this. And it predicts both of these simultaneously, right? So that's the output of the model. If I train on barium titanate, that was equilibrated at 400K, and then it has 135 atoms, so that's quite a lot of data per structure. But I only have 50 structures of these, so there's only really 50 training points that I can ever show the model. The results that I get are like this. So the blue is just the distribution that's found within the data, right, between the tensors. In this case, it's the Raman tensors. So I'm just going to calculate the difference between all pairs of tensors that's found in the data, and I get a histogram like this. The reason to do this is because I can't draw a parity plot because I don't have a single number, I have the whole tensor. So I just look at the differences in the data, and then these are the predictions made by the model, right? There's both the training and the validation, which is the important part. So the difference between the prediction made by the model and the actual label is all plotted down here. So obviously 0 would be perfect. And the fact that it's very well separated from the distribution data tells me this is performing very well. And it's already performing well on just 10 out of the 50 of these structures. And similarly for the Born effective charges, right? The distribution is down here. So we're able to predict these with a good level of accuracy. Then I wanted to see, well, what happens if I start with, these are the ones I showed you on the previous slide. I reduced that further to just 4 training structures. Actually, for the Raman, it's still pretty good. The Born effective charges are getting worse. And then as I show it less and less data, okay, it turns into something that's no longer useful. But already with 4 structures, we're doing very, very well, and we can sort of balance this to make this one better, that one slightly worse. So it's actually, again, showing this property of what I would think is quite a high level of data efficiency. 4 and then predicting on 46 structures is already pretty good. So the next step that we're working on now is to inject even more physics into this model, where you can input the electric field into this neural network here and predict the enthalpy directly. And the reason to do that is that the model that I just showed you, these 2 quantities are just spat out by the model, but there's no physical link between them, insofar as if I take the derivative of this once more with electric field, I should get this guy. But in the previous model, there's nothing to constrain that to happen other than just the data. By doing it like this with the electric field as an input, we can take the derivatives using automatic differentiation, predict these quantities, and then train the model on that to reproduce that perfectly rather than the way we did it. And so that's a work in progress at the moment. And then those would be mathematically linked by the derivative that we know links the 2. That was electric response. We can also look at magnetic. So if we apply a magnetic field, we'll also see a response as we would do it in, say, an NMR experiment. NMR shielding is a shielding tensor is just going to look like this. So the derivative of the enthalpy with the magnetic field this time, and the positions of the atoms. And this is again a rank 2 tensor, so I can play the same game I did before, and put in my atoms and positions and spit out the shielding tensors. This time we had a data set that was quite heterogeneous in terms of the chemistry, so it's all silicon-29 shieldings, 56 structures, so relatively little data, and a lot of different elements in those structures. 80-20 split, and my student Mattia that I showed on the previous slide did this very similar model, and you can see there's a lot more overlap here. Now this is on a log scale, so it's actually not as bad as it maybe looks. We tried to stretch it so we could really see what's going on. But clearly the performance is not that great compared to what we had before. And I think a big part of this is really this chemical diversity. So, and this is a general thing that everybody's seeing, right, when fitting interaction potentials or anything else. If you have a large part of the periodic table but very little data for each part of it, you're going to struggle to make very, very good predictions. Unless, for example, you start with a model that's pre-trained for another property and then maybe try to transfer learn to something like this. So I think that would be the next step for this, as well as just augmenting the size of this data set to try and get better predictions for shielding tensors. Okay, let me wrap it up there. So I think hopefully I've made it clear that these equivariant neural networks, yes, they are costly, they're going to be more expensive to train, but they will give you significantly better data efficiency. But not only that, they will also give you a flexible way to express the ability to predict quantities that are just not possible with these invariant models, either as inputs or outputs of the model, or both. And particularly for the Hubbard parameters, this is now getting us down to 3 to 7% accuracy on these. So we're making a hundredfold saving in the computational cost and getting pretty much good enough for any high throughput screening that we want to do. And it transfers well to other systems, chemistry that it hasn't seen before. And we're currently calculating a lot of these, many hundreds of different systems with transition metals to get training data to provide the community with a general purpose tool where you can just put in your structure, get out the Hubbard parameters, and use those without needing to do that part yourself. And if you want to see the preprint of the work, it's just there. Finally, let me just thank Nicola Marsari, with whom I worked on a lot of the earlier stuff, Tev Schmidt and Mario Giger, who I work on the equivariant neural networks with, and of course all of my funders for their support. Thank you for your attention.
So questions? I have one to start. So about this Hubbard estimation, one thing that I wanted to explore is on slabs. I don't know if the U could vary depending on if you are in the surface or deeper in the slab. So your model would be able to do that for, well, it's the same atom, but should be a different chemical environment for the surface and the bulk one.
Yeah, so the model will for sure see it insofar as the oxidation, the occupation matrices around will change.
Yeah.
If you only train it on bulk and then ask it to, predict on the surface, it might struggle, but it might not, because the oxidation state might look like something else that was in bulk, but in that oxidation state. So it might actually perform okay. And I think that's the big advantage of this model. It doesn't need to know anything about the atomic species and learn those things. It can just learn about the electrons, which are just one species. And so long as it's seen that in, say, a delithiated structure on the surface, if it looks similar, it'll get it right.
Yeah, but then if I absorb a molecule, then it's diversity and...
Yeah.
Okay.
And this will particularly be true for elements that have a wide range of oxidation states, right? Here we only have two plus, 3 plus, but you can have ones that can go easily in 3, 4, maybe even 5 different oxidation states. So.
Okay, questions? Don't be shy, people. Just ask.
So on that one that you're trying to get the enthalpy first and then you derivative, are you using like the physics-inspired neural networks where you put the enthalpy in the loss function and then try to minimize that?
So the loss in this will have, the enthalpy, but also the tensors themselves, right?
Oh, okay.
So you predict the enthalpy, then you use autograd to get the tensors, the prediction tensors, and all of that goes into a sum in your loss function. So you try and balance getting all of them correct.
Yeah, okay.
And you can think of that as being the same as like you predict an energy and forces. So you're trying to get a function and its derivative correct, and higher order derivatives. So yeah, that's the plan.
That's very good.
More questions? Oh. Excuse me.
Hello, Martin. Thank you very much. I really appreciated the presentation. I don't know if I understood it right, but is it the point of the equivariant models to better predict molecules' energies in substitution of the DFT calculation? This is the point?
So there's several things. So one is, yes, to predict energies or other scalars with a higher level of precision or with a lower amount of data, for sure. The other point is, with a non-equivariant model, you cannot predict tensorial properties, right, unless you take derivatives directly. So you can't predict a tensor like a Raman tensor directly. You can predict eigenvalues of one, but you can't predict it. So it's whichever one you want.
I have one more question. Since it could substitute the very expensive DFT calculations, you showed the application to use it to predict properties. But could it be used to predict new materials? Because the energy calculation is very important for it, right?
Yeah. So, I mean, you can sort of go both ways. You can do, for example, structure prediction by searching through the energy landscape that you fit the potential to. That's okay. You have to be careful because you might wander out of where you've trained on, and then it might start to become meaningless. Then the more difficult part is, what if you just want to predict the atomic positions in a single shot. You don't want to explore, right? And for that, you really need the generative models. So I've got other slides about this, but it's not as easy as just using a model like this to, you flip it around and predict atoms. You have to do a bit more work to integrate methods like diffusion modeling, which is used for, say, the image generation, like Midjourney. But yes, absolutely, you can do that, and that's something that we're working on. But let's say it's something that's a few steps away.
Okay. Thank you very much.
Thanks.
More questions? So, no more questions? Let's thank the speaker again. Thanks, Martin.
Thank you.
So that's it. Thank you for coming, people. Hello?